Okay, so I'm going to start. So the first part of this afternoon session is about manipulating this data either with polynomial moment problems or Sdp. So the first thing to do, if you haven't had the time to do it before, is to basically install the package, the Julia package, polynomial moment optimization.jl. So this is the command line to do so. And you will also need for this tutorial to have the dynamic polynomials package installed. So you should try to install both of them. And if you have troubles, please shout or ask questions in the chat. So I would basically prefer that you interrupt by speaking, because I don't always have a look at the chat. Okay, so this is the first thing to do. And once it's done, so this will be for the last part of this afternoon session. Basically, we'll be able to play with the database. So basically pull what is in the database, but also push. And this is done via Git. So this was the first tutorial of this morning. But to be able to push, you have to be registered in the GitHub project. So in the same way you are maybe registered in the Poema Workshop GitHub project, you will have to be also registered in the PMO project. So for this, you can either send an email to Bernard, or you can also send your GitHub login in the chat. And then there are various commands to simplify the Git access. So should we put a link to the slide so that people can copy paste the comments, or is it better if I just give the comments to copy paste in the chat? Because there are answers to the exercises in the slide, so maybe we don't want to share them right now. Okay, let me just at least copy paste the link to the tutorial. Okay, so let me do that. Up. Okay, then you can play with the copy paste directly. Okay, so basically there are three types of problems that you can define with this Julia package. So the first one is an optimization problem involving polynomials. The second one, moments, and the third one, semi-definite programs. So in each case, you have to define an objective function, optionally, sign constraints, so greater or equal or less or equal, and or equality constraints. So this is very standard practice. So let me start with the first one. So the first one is polynomial data. So here we either minimize or maximize a polynomial that is defined with the package dynamic polynomials. And then you have a bunch of constraints. So you can have inequality constraints or equality constraints. So in the slide, they are just greater or equal, but you can also put less or equal. And so this is what we call sign constraints, but they are actually inequality constraints. So we're going to play a little bit with the database, and we're going to add this one. So it's a completely artificial problem. I'm not sure it comes from an actual application, but if you have if you want to add your favorite polynomials coming from your favorite application, then you can add a similar one. So in this case, we minimize a polynomial of degree 4 in two variables, and we have two sign constraints. So the first one with less or equal, the second one with greater or equal. And the last constraint is an equality constraint, just involving one variable y. So here is how you can do that. So after installing PMO and dynamic polynomials, you basically load the two packages with the using command. And once you did that, then you will define all the data of your problem. So the first thing to define is the variables. So here you have two variables, x and y. And then you define the cost. So this is exactly the polynomial that we saw on the previous slide. And then you define the three polynomials involved in the sign and equality constraints. So G1, G2, and H1. And then you have this comment given by PMO. So you will basically call the method from PMO by doing this PMO.polynomial. So you specify that it's a minimization problem by putting inf. Otherwise, you would put sup. And then you just give the two sign constraints and the equality constraints. So basically, this first comment, f equal PMO.polynomial blah, 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 defines you the object f. But then you can play with f. You can modify it. So for instance, you can add a documentation to f. So here it's a simple one, first polynomial example. But you can also define afterwards the different attributes of f. So you can add a name, for instance. You can add ideas and so on. So we will have a look at the different attributes now. So I'm just gonna check if there are any questions in the chat. So there are no questions so far. If you have one, please don't hesitate. We want this to be as interactive as possible. Okay. So you can alternatively define the same data f by replacing PMO.polynomial by PMO.data. But here you need to specify that the data that you add is a polynomial one. So if it would be a moment, then you would replace type equal polynomial by type equal moment, and same for SDP. And so the Julia output is the following one. So it is a model, and it has several attributes. So the first one is the type. It tells you that it's polynomial, gives you the list of variables, the number of variables, the constraints, the objective function, the version of this model, and an ID. So just to summarize the different attributes you can play with, so you can modify basically all of this. Of course, when you modify it, it should be quite consistent. So meaning that afterwards, when you will use this data for to solve optimization problems, everything should be consistent. Otherwise, you will basically do nonsense optimization things. And so these are basically the data, the attributes that I mentioned before. So type variables, number of variables, objective functions, constraints, and so on. So for instance, if you want to modify the version, you can just type p double colon version and so on. So you can also be very brutal and remove attributes, but this is highly non-recommended. Any question on this so far? So has anyone troubles to install and load the two packages? So everyone succeeds to install and load the two packages. Okay.
Well, I got it to work, but if I just import, sorry, I'm going to echo. If I import just the code as given in the slides, I get an an error of some sort in my packages. Let me see if I can copy it.
Yeah, sure, please go ahead.
I don't know if that is just for me.
So for which one? For PMO or dynamic polynomials?
That's for PMO.
Okay. So did you type bracket and then add with the GitHub link?
Yes, in the REPL.
Okay.
I also tried the alternative, which was the pkg.add and then brackets, quotations, and then the HTTP, but same problem. But I got it to work regardless.
Okay. So are you sure that you are in the package environment when you do the add function?
So yeah, that's what I assume. So I git clone it. Okay, I don't know if I should waste too much time on this installation aspect, but yeah, I git cloned it. I went into it. I activated the package environment, and then I tried the pkg add thing, but it didn't. And I just tried using PMO, and it loaded, or it compiled.
Ah, okay. So
it works.
all right.
Yes.
Okay, so if it works like this, then it's fine. So okay, Felix also had an issue. So which version of Julia do you have? Is it 1.6.0?
I think I'm on 1.5,
Okay.
1.52 or something.
Okay, and Felix, is it the same for you? Okay. So maybe, I mean, I had issues with versions less than 1.6.0 as well. Maybe not for this, but for further manipulation. And then I just basically switched to 1.6.0 and all the issues just vanished. So that might be okay. That might be a brutal way to fix this, but for me it worked. Okay. So Bernard or the others, does this error ring a bell for you? So
it seems that this is a message saying the package URL or URI is not there. But if you install it with add with a bracket add and then the GitHub address, it should install all the other packages that are needed.
Okay, and I also suggest to do this thing. Because sometimes it solves package conflicts basically. So for me there is no change, but there might be some changes for you as well. Okay, let me move to the further type of data. And also just before, so there is this nice write and read functions which allow you to print and save objects from the database to the JavaScript object format. So it is, yes. Oh, no, okay. So it is basically quite hard to read the JSON format. So, but it's a nice intermediate when you want to use optimization tools afterwards, or if you want to do translation between the Julia and other programming languages. So one way to do it is to simply write the model you just defined. So you can either write it in order to display it on the screen, or you can write it on a specific JSON file. So here's an example. And you can do the opposite operation. So basically you can read a JSON file with the read command. And then you can display it on the screen if you do write up G. So the second type of data is moment data. So it's a bit similar to the polynomial data. So the objective function is a sum of integrals. So it's yes. No, okay, I'm hearing some noises. Maybe someone didn't mute his mic. Okay. Yeah, so basically the objective function is the sum of integrals. So in each case, you are basically integrating polynomials with respect to some measures. So the measures are given by mu1 up to mu nu. So basically afterwards, you will just define all these polynomials and then specify the constraints. And then what is a bit more delicate here is that there are two types of constraints. So you still have this sign or equality constraints, but you can directly define inequalities on a big, let's say, number of moments. So this is done with this star operation. Okay, so the star operation tells you that when you do G star mu, all the corresponding moments which are here, so mu, the integration of PQ against mu should be either non-negative or equal to 0. And you can add many of them. So here it tells you that for each polynomial Q, you will have an inequality or a corresponding equality. So this is one way to encode an infinite number of moment conditions. And you can also give a finite number of moment conditions, so inequalities or equalities. So for this, you do exactly as for the objective function. So you have a sum of integrals plus a number, which is either greater, less, or equal to 0. Okay, so are there any questions in particular on the difference between the two types of constraints? No? Okay. Let me first give an example, and then I will talk a little bit more about what you can and what you can't model with this this second type of data. So so it's also a very artificial example. It actually uses some of the polynomials that were used for the first polynomial data example. So here we have two polynomials involved in the cost. So the same one as previously, and the polynomial xy. And we are integrating these two polynomials against two different measures, mu1 and mu2. And then we have these two types of constraints. So the first one gives an infinite number of moment constraints. And the second and the third one gives just a condition on infinitely many moments of the measure. So the first inequality tells you that when you integrate x with respect to mu and you remove 1, then the result is non-negative. and the last one is an equality constraint. So, so it's very similar to the polynomial data. So you define all the polynomials involved. What is a bit tricky is that you need basically to specify a difference for the two types of constraints. So when you want to encode the star operation, you just say that it's greater or equal than 0. So this is what is written here. And when you have a finite moment constraint to specify, then you add the star. So this is the convention we decided to have. And something important also is to put these zeros here. So in the cost, we are integrating mu1. We are integrating f1 with respect to mu1 and f2 with respect to mu2, and then we add both. So you need to define a vector of two polynomials. But if you go to the first inequality constraint here, you can see that mu2 is not involved. So it is equivalent to doing this plus 0 star mu2. So that's why we need to put a 0 afterwards. And it's the same here. So here we are not considering any moment of mu1. So we need to put a 0 first. Okay? Is it clear? Is it clear for everyone how to encode this moment constraints? Okay, if no one is complaining, then I will go on. And no, okay, so just one thing. So for some people who consider a linear problem over measures and not linear problems over moments, I think at the moment it's not possible with the modeling tools that we have, but it should be available soon. So for instance, if you want to say that mu1 is non-negative, then I think it's not possible with the current modeling tools. And the last type of data is the Sdp data. So here we have a linear cost, so defined with the vector cost f, and we have a bunch of linear matrix inequalities. So here we need to basically specify all the matrices which are in front of each variable xj, and potentially a constant matrix here. And since Sdp includes LP, then we can, of course, add some linear inequality or equality constraints. So again, I will show you a simple example. So here we have an Sdp with 3 variables, x1, x2, x3. We have 2 linear matrix inequality constraints, and we have 2 linear equality and inequality constraints. So we have in total 4 constraints and 3 variables. So here you can note that there is no term involving x2. So basically the matrix in front of x2 is 0, and there is no constant matrix. So it's again 0. And in the second LMI, there is no matrix in front of x3, so it's like it's 0, and so on. So so for this, you will need to use the linear algebra package. So you will need to install it if it's not done, but it should be with PMO, I think. And of course, to load it. And so basically, you will, as the polynomial and the moment data, you need to define all the matrices, all the matrix data. So I don't know if you are familiar with this symmetric operator. So actually, this matrix is not symmetric, but when you apply the symmetric operator, it transforms it into a symmetric matrix. All right. And so, so here the first LMI, we have two non-zero matrices. So this one is for x1. So there is a 0 in front of x2. This is for x3. And actually, that's it. But we could have put a 0 here after to explicitly say that the constant term matrix is 0. But you don't need to do it. Okay. And then we have similarly the second LMI with the matrix for x1, the matrix for x2. The one for x3 is 0, and this is the one for the constant term. So you define your two LMIs, and then you can define the Sdp problem. So this is the cost vector. So x1 plus 2x2 plus 3x3. This is a minimization problem. These two conditions says that you have the two LMIs. And here you define, in the same way as for the cost, you define the linear equality constraint and the linear inequality constraint. So you give the coordinates of the two vectors here. Any questions on that? Okay. Still have no questions. I hope you are still not stuck with the installation of the PMO package. So okay, so this is for the Sdp. There is actually one more thing that we wanted to tell you about this Sdp, is that you can actually model low rank matrices quite easily by using tensor products of vectors. So if you want to encode a rank 1 matrix, you can use this this tensor product vector trick. So here we just have one LMI. So as before, we have a matrix for x1, a matrix for x2, and this matrix for x3 is a rank 1 matrix, and you can define it with this tensor product. So to encode the LMI, you do as before for first and second matrix. And here the constant matrix also is encoded like this. And to encode the tensor product, you can just specify the vector. So here it's the vector 0, 0, 1. So you could replace this single tensor product by a sum of tensor products by just adding the coordinates of the other vectors here. So here, if you put a comma and the second vector, it will basically give you a rank 2 matrix defined from these two vectors. And then, as before, you say that you want to minimize something. So here it's x3 under this LMI constraint. Questions about that? Okay, and so basically this is all the slides that we wanted to show. So now what we propose you is to create a PMO data with your favorite example. So maybe you will succeed to do it immediately. Maybe you won't because there is a bug in your modeling. Maybe you won't be able because the modeling power of the PMO is not large enough yet. So please try to add something, and we'll try to help you if there is a problem in the remaining time. So I will try to add one as well. So here I loaded PMO and dynamic polynomials, and I will add the polynomial problem. So I will define a polynomial problem in 3 variables, x, y, and z. And then I will take the square of the sum. So I like this polynomial for a specific reason. I will tell you more after. So I have 3 constraints. So each variable lies in -1, 1. I need to tell for each variable. So I need to define 3 polynomials for each constraint. And then to add this to the database, I will define it like this. So I want to minimize f under the constraints that each variable is between -1 and 1. Okay, so it seems to work. And then I will give a name to this guy. So first I can check Okay, I can check the number of variables, so it's 3. I can check the type, it's polynomial. I can have a look at the objective. So the objective is minimization of this square. So actually I think there are 2 elements in these attributes. So the first one is the objective polynomial itself. Second one is that we want actually to minimize it. And I think there is no name right now for this guy. Okay, it's big F. So I will give name. So I will call this guy dense not sparse. Okay, so the reason I call this guy dense not sparse is that actually we can write this square as a combination of the 3 gj with dense sum of squares multipliers. So it's basically, it has a dense Putinow representation, but it's not true when you try to do this in the sparse setting. And I think it's one of the simplest examples which prove that you cannot always use sparsity under general assumptions. Okay, so does anyone want to share his try to add something in the database? Or to create a database entry? If you have bugs or if you have troubles, please interrupt, please ask.
So this may be a silly question that I missed.
No, please go ahead.
Now that we've built these sexy models, how do we run it or optimize it?
Oh, this is going to be the topic of Bernard's presentation at the end.
All right, cool.
So we'll basically show 2 ways to solve the optimization in the case of polynomials. And I think maybe Michal will show something also in the Sdp case.
Not entirely, but may I have a question actually elementary question to Julia. If I store, let's say, the LMI1, LMI2, that model, if I store it in a file, how can I call it from Julia? Can I, like a MATLAB script, I mean?
So it, what do you mean? You mean that you already have something encoded in the JSON format and you want to import it to be able to read it within Julia?
I copied from your slide this LMI1 equals symmetric and so on and so on. These Julia commands. I stored them in a file, because then I don't want in Julia terminal, I don't want to repeat it all the time. So
sure. Well, then you can use one of the editors that was mentioned this morning, or you can simply write the commands in the JL file as okay. And Bernard then gives the command which allows to include, basically to load the contents of the file. So you can use, for instance, include and the name of the file.
But can I do it locally on my computer? Because
Yes.
I stored it in a file, something called JL.
Yes.
And now I want to call it, but
yes. So let me show you an example. So for instance, here I have basically I copy pasted all the commands of the tutorial in this tuto.jl file. And if I want to read this file, then you need to do include and then the path.
Oh, okay, yeah.
So here I am not in the correct repository, but I can basically go there. I think it's here. Oh. Yeah, and then if I press enter, I will load everything that is in the file.
Yeah, and it works here as well. Yeah, include. Thank you.
Okay. Is there a function for checking whether a polynomial is SOS without implementing the SDP? What do you mean? You want to avoid SDP to solve an SOS problem, or you want to use an available SDP solver? So there is a second question, but maybe I'm going to wait for Luis to specify a little bit more what he means in his question. Luis, if you want, you can unmute yourself and talk. Okay, so meanwhile, I'm going to try to see.
Can you hear me?
Yes, yes. So what do you mean exactly?
Yeah, so I want to check if one polynomial is a sum of squares, and I don't know if there is one solver which, one function that's. Yeah, so I don't know if I need to implement the SDP, or if there is one available function for checking that.
Yes. So there are several packages to do this. So there is one in particular which is called sumofsquares.jl. There will be a specific lecture on this solver during the next learning week at the last week of June by Benoît Legat. But I can give you the pointer if I find it. Okay. Let me just check that it is the right one. Yes, it is.
Okay, thanks.
So this is one.
Also, do you know? So the performance of this method, so to identify, I don't know, a polynomial with how many variables and the degree?
So I mean, the performance at the end depends on the performance of the SDP solver. If you don't put additional information to the solver, then he will just run the so-called dense relaxation. So basically, you can the magnitude of the data you can have is basically up to 8-10 variables and degree 8 or 10. Now, if your polynomial has some specific property that you can exploit, so sparsity or symmetry, then you can get much better performance. So you can use, for instance, the Tensor solver. Let me give you the link. So it is actually a tool to solve optimization problem, but you can basically compute SOS decompositions if your polynomial is positive or non-negative, and it automatically finds the sparsity structure.
Okay.
So in some cases, it is much more efficient to use this.
Yeah, thanks.
So in the sum of squares package, you can actually specify the sparsity structure more or less. It is a bit similar to YARMIP in MATLAB, but yeah, it doesn't do it automatically, let's say.
Okay, thank you.
The second question, hello, I followed through the example on the slides. Method error, no method matching JSON polynomial terms. Okay, Andrew? Are you there?
Hello, can you hear me?
Yes, I can hear you. All right, so
I'm wondering maybe it's just because I haven't got 1.6. I've got a previous version as well, but
no,
I just found it strange that the previous example worked. But
so I don't know. Okay, so it is okay. It wasn't with the example from the slides. It is with your own example, right?
Yeah.
So can you give the command? Can you copy paste maybe the command lines that you tried?
Sure. Oh yeah. Well, with let's start.
Okay, let me try. Okay, this chat thing is very capricious. So, okay, maybe I can find a minimal example which is similar to this in the remaining time. So, okay. No, but I think in the case of Andrew, everything is rational, so it should be fine. So I think maybe the problem comes from h minus e times p equals 0. Maybe you should define first one polynomial which is equal to h minus e star p, and then say that its polynomial is equal to 0. Maybe.
I tried that as well, but it didn't. I got the same error.
Oh, really?
E plus 0 equals. Oh, Bernard's suggestion works if I do E plus 0.
Okay.
Thank you.
Oh, because E is considered as a polyvar and not as a polynomial.
Oh, I see.
Yes.
Yeah, sometimes it happens. It's a bit annoying. So there is not really automatic translation of types as you can have it for plus or whatever. Remy, I maybe miss it, but is that possible to use non-rational algebraic coefficients? Well, in the example that we showed, we had basically a polynomial with floating point coefficients. I'm not sure. Oh, well, Bernard, can we add any?
Maybe I can, yeah, speak.
Polynomial?
You hear me?
Yes.
Ah, cool. I was like thinking about like doing exact computations because, like, for example, if I put the exact pi, it does not work. And
yes, it doesn't work with pi. Yeah.
I try to use, like, for example, the square root of 2, but I don't know how to write the square root of 2 in the exact way.
Well, yeah, I don't know if dynamic polynomials allows you to manipulate any type of coefficients.
Okay.
There might be a way to do it, but at the moment I don't know.
Okay, thank you.
So maybe it's worth looking at the links that we sent before about the symbolic computation in Julia also.
Ah, yeah. Yeah, thank you. I will investigate.
Yes, so the coefficients, it's building some polynomials, and the coefficient here could be integer or big integer, rational, floating point, big floats. But algebraic numbers, I don't know.
And
The way
because I was thinking about like doing computations in algebraic extensions.
yeah, so then you need to introduce variables and some new polynomial constraints.
Okay.
Yeah, of course you can do it like this, but you can have Andrew problems also with yes, exactly. So I think, yeah, if you have a variable or if you have a monomial, then or a constant, then it might not work. You really need to have something of type polynomial in order to make it work. This will also be the case when you use the sum of squares package in Julia or the TSOS package in Julia. You will always have this problem.